Hello and welcome back to Algebra, the video series where we talk a lot about group theory. And indeed, in today's part 16, we will continue our discussion about cyclic groups and show that every subgroup of a cyclic group is cyclic again. This means if a group is generated by just one element, all the subgroups are also just generated by one element. However, as always, before we try to prove it, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter you can download a lot of additional material with the link in the description. Moreover, before we dive into our discussion about cyclic groups, I want to give you some additional information about calculating with integers. The integers is a number set denoted by z, and we already know it's a group. In fact, it's a cyclic group and generated by 1. And therefore we find something nice there, which is called division with remainder, or sometimes also called Euclidean division. It's something really basic and natural, but we will need it very often, and therefore I want to prove it now. So we already know every element in Z can be generated by the one element, which we could illustrate by putting these 1 boxes in a row. So we could say our integer a looks like this. And on the other hand, we could have a second integer we call b. And now the Euclidean division means that we can do the division a by b and get a remainder that is smaller than b. This means we would take as many b's as we need to almost fill up our integer a. So in this case, you see we have exactly 5 times b and a remainder of 1. So maybe not so surprising for you, but definitely something we will need for our cyclic groups. So the first thing we can do is to formulate this division by remainder with the correct terms. Here we have 2 arbitrary integers a, b and z, and b should be positive. Indeed, we could also include the negative numbers, but we have to exclude 0. Okay, and now with this formulation, we get the existence of this multiple and that remainder. And in fact, we also get the uniqueness, so there's only one pair that satisfies this division with remainder. And the common notation is q and r, so we get 2 integers out. And these 2 integers should satisfy that we can rewrite our integer a. Namely, a should be given as q times b plus r. And moreover, our remainder r should be the smallest possible one, but still non-negative. So the best case would be that this remainder is equal to 0. And on the other hand, the worst case would be that it is almost b, but it cannot be equal to b. So there we have it. This is the whole formulation for the division with remainder in Z, and now we can prove it. The proof is not so complicated because we just have to show the existence and the uniqueness. And maybe let's start with the uniqueness, because it's quite simple to see that there can only be 1 multiple and 1 remainder with this property. And in order to see this, let's assume that we have 2 different pairs, q1 r1 and q2 r2. However, since a and b stay the same, we have the equality of the right hand side here. And now the natural thing to do would be to bring the remainder terms to one side and the multiple of b terms to the other side. So it's just a subtraction which we can do in the integers and not complicated, as you can see. And moreover, on the left hand side we can also use the distributive law to factor out b, which means the difference of the 2 remainder terms is given by a factor of b as well. However, both remainder terms here satisfy this inequality. And this means that we get a lower and an upper bound for the difference r2 minus r1. Namely, the most extreme case would be that we have to subtract b or that we have to add b. So this difference definitely lies between minus b and plus b, but we don't have equality on both sides. So the conclusion is that our multiple on the left, which is an integer, cannot be plus 1, cannot be minus 1, it can only be 0 to satisfy these inequalities. In other words, q1 has to be equal to q2, and therefore also r1 has to be equal to r1. And that's exactly what we wanted to show. We have uniqueness of this decomposition. And then we can immediately go to the existence, where we have to construct this unique solution. In fact, this is not so complicated if we already know how to do division with the rational numbers. In the rational numbers we don't have any problem because we can just write a divided by b and we know it's a well-defined rational number. This is not the division with remainder because here we actually leave our integers. However, by the construction of rational numbers, we already know that the integers are just special rational numbers. So you could say the integers also lie on the rational number line. And with that knowledge, we can show that any rational number lies between consecutive integers. Indeed, this follows from the Archimedean property of the rational numbers. More precisely, we can put it that a divided by b can be equal to q, but not equal to q plus 1. And otherwise, it should just lie in between. Okay, when we have that, we can simply go back to our integers by just multiplying with b. Then we just have our a in the middle and the multiples of b on the left and on the right. Moreover, then you see we can just subtract q times b everywhere and then we have 0 on the left. And in the middle we have a minus q times b and on the right we just have b. Hence you see this is exactly our remainder term which we should call r. And then we have it. With this definition our decomposition is complete. We have the division with remainder. More precisely, we immediately get that a is equal to q times b plus r and r satisfies the condition of the remainder. So the proof is done and the division with remainder is no problem for us with integers. However, now you might already guess that this property can extend to other cyclic groups. Indeed, now we can go back to our theory of groups. Let's consider a general cyclic group. So we have our group G here, which is cyclic, and as stated at the beginning, now we know that every subgroup of G is also cyclic. So in that case we have an implication, U as a subgroup is also cyclic. So please note, this means that U is also just generated by one element. And this is what we can prove now by using the division with remainder from the integers. And why that is, you might already see, because G can be written as the powers of one element. And these powers k just go through all integers in Z. And here please note, for the rest of the proof, we fix our generator G. You already know this generator G is not unique, but we can just take one. And now the question is simply, what is the correct generator for our subgroup U? In general, this should not be our lowercase g, because otherwise we would get back the same group G. So if we have a non-trivial subgroup, we should find a different generator. Speaking of trivial subgroups, the case that U only consists of the identity element is also not a problem. What I mean is that this group is definitely also cyclic. In other words, we don't need to consider this case in the rest of the proof. Hence, from now on, we can just assume that U has at least two elements. So we can ask the question, how does the subgroup U look like? Of course, it contains the identity element, but every other element looks like G to the power k. To keep it general, we could say we have the power k1 in this case. However, since the whole thing is a subgroup, we also know that the inverse with the power minus k1 is also in U. Therefore, we don't lose any information to assume that our k1 is a positive integer. And now if we have more elements, we could say we have the power k2 and the power minus k2, and the same with k3 and so on. And now the important thing here is that we work with positive integers and we know there has to be a smallest one. And I would say, let's call this minimal integer m. So it should be the smallest natural number such that G to the power m is still an element in U. And to emphasize here, the natural numbers don't include 0, so m is definitely greater or equal than 1. We know such a power has to exist, because our subgroup U consists of at least 2 elements. And at this point we can just consider any other element in our group U, which means it's g to the power L. So L has to be an integer as described before, such that this one actually lies in U. In the case it's a positive integer, we know that it's larger or equal to m. Hence we can just divide L by m and do the division with remainder in z. This means we can write L as a multiple of m plus a remainder. And we know the remainder cannot be equal to m, but it could be 0. Actually, we will show now that it has to be equal to 0. This is because of the subgroup property, because we can use this decomposition in our exponent for the generator g. So we can just calculate g to the power r, which is definitely an element in our group G. However, now we also know that this is g to the power L minus q times m, which can be rewritten as the element g to the power L times g to the power m to the power minus q. So you see, these are 2 elements of the subgroup U, and the second one is just an inverse in U. Therefore, this combination of subgroup elements is also an element in the subgroup U. And there you see we don't have many possibilities for R. Either R is equal to 0 or it's bigger than 0 and less than m. But in the second case, m would not be the smallest natural number where the power still lies in U. So the conclusion is, since m is minimal, R has to vanish. Which also means that the division with remainder is actually without a remainder. Hence every integer L we can use can be actually written as a product q times m. So no matter which element in U we choose, we see it has a very special form. Namely, it's g to the power q times m, where q is an integer and m is our minimal chosen natural number. And there you see, we can write it as g to the power m to the power q. And obviously you see, if q is any integer, we will not leave our subspace U, and therefore our g to the power m is our generator. Indeed, what we get is exactly the equality. U is equal to the subgroup that is generated by g to the power m. And that's all we wanted to show, because we see that U is a cyclic subgroup. So our result is that inside a cyclic group, all the subgroups are also cyclic. And as you have seen, this was just a division argument, nothing more. So quite nice to see the properties of the integers translate to a cyclic subgroup. Okay, maybe that's good enough for today. Let's see what we can do with that with the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.